So I guess what I want to move on to in the second part of the presentation is the other way we can use geothermal, which is for heating and cooling. And the reason I like this a lot is because its potential is very geographically widespread. It's much less limited than deep geothermal for electricity generation. So we're going to move now into this shallower domain, looking at the upper few hundreds of meters typically of the Earth's crust. And I think it's rather the unsung. Most people, when they think of geothermal, they think of electricity generation, they think of the geysers, they think of steam. But I think this has, in some ways, more potential to make a big contribution to low carbon energy generation around the world. So, if we talk about kind of medium geothermal, this would be temperatures high enough to use directly for heating. And this takes us back into sort of deep sedimentary basins and so forth. So this is a map of Germany, Munich down here, and this is the reservoir that we talked about before. And often medium geothermal for heating is kind of right at that cusp between, is it hot enough for electricity generation, or is it only going to be hot enough for heating of buildings? And the real thing we struggle with here is maintaining those porous and permeable aquifers. It has some shared problems with hot, dry rocks. We want to have naturally porous and permeable aquifers. You know, this Malm aquifer is a little bit unusual because it was preserved to these relatively significant depths, about 5 kilometers here. I realise for those of you at the back, this must just be occasionally a bit of a vague image you're getting. I didn't realise I should have made these much bigger, but I do apologise for that. And there are plenty of places where we've tried drilling wells to these kinds of depths to produce geothermal energy for heating, and we found the rocks are dry and we found the rocks are impermeable. So there was an example of that in the UK. There was a well drilled on Newcastle. It was intended to be an open loop well that would heat a whole series of buildings at the surface, but then when they tested it, it was dry and it didn't flow at all. So we've had some failures where we tried to target some of these deeper sedimentary rocks to bring heat to surface from them. What we can do instead is to stay shallow and use a heat pump. So if we look in the very shallowest part of the crust, so now we're only going down to, this is sort of 400 meters here, in the upper sort of 100 meters or so, in fact the temperature stays around about constant. It doesn't really fluctuate very much. If you go right into the upper part, it will get warmer in summer and cooler in winter. But then once you get below about 10 to 20 meters, that heat exchange doesn't penetrate so deep. And so the water and the rocks here are typically always around about sort of 13 or 14 or 15 degrees or so. So whenever I drill, whenever we work with a borehole in London, for example, in the chalk, it's always about 13 degrees. Now, that doesn't sound very much, but it's warmer than cold outside air in winter. So if you can bring that water to surface, it has energy in it you can use usefully for heating if you boost it with a heat pump. It's also cooler than the outside air in the summer. So if you bring it to surface, you can use it for cooling. And that's really the basic principle of shallow geothermal. But we would boost those temperature changes using a heat pump. Now, again, when we apply this technology, there are several different ways we can do it. The one that most people are familiar with is what's called a ground collector, where your back garden is dug up and a whole load of pipe work is put in there and it's connected to a heat pump in your individual building. I'm not going to talk about those today, and actually I personally think that this is probably not the right route for us to be going down if we're going to deploy shallow geothermal in a very widespread way. I want to talk about systems that are much bigger capacity than that. So these would supply major buildings like hospitals or schools or universities, and if you want to use them for domestic use, you would do it via a local heat network. And in fact, there are even now companies looking into doing this where you would drill some boreholes on your street and they would basically come and sell you heat as a service rather than the fuel to generate your own heat. So they would then pipe to you from the boreholes groundwater or some other working fluid that would provide you with this feedstock that you could then boost with your own heat pump. And again, we can do this either with a closed loop borehole where the fluids remain within the borehole itself, there's no exchange, or we can do it open loop where we actually produce groundwater. So as a quick aside, because I'm often asked this, what is a heat pump and how does it work anyway? Okay, So I know this is a geological association, which we're going to have 2 slides diversion on just what a heat pump is. I think the name of heat pump is really misleading. It doesn't pump at all. And we all have a heat pump in our house because we all have a fridge. And essentially it uses the same technology as a fridge. So what we do is we have our source of groundwater, for example, that's coming out. And if we're going to use this for heating, we have a fluid with a very low boiling point. And so just adding that bit of heat from the groundwater is enough to cause it to boil. And then we pass it through a compressor, not a pump, we compress it. And that's where the electricity supply comes in. It's to compress the gas, and as you compress it, its temperature goes up. And so then you pass that high temperature via another heat exchanger into the fluid that's then going to heat the building that you're in. That cools the gas, which then recondenses, and it passes back through the heat pump where it's boiled again, and so on and so forth. And so it should really be called a compressor or something like that, rather than a pump. And the thing with heat pumps, and I think this is something that most people are aware of, is the less you have to change the temperature, the more efficient your heat pump will be. So heat pumps are measured, how well they perform is measured by something called the coefficient of performance. And that's the ratio of how much heating energy comes out to how much electrical energy goes in. So a good heat pump will put 4 units of heating energy out for every unit of electrical energy that you get in, which is why it's so much better than using a direct electrical heater. Your kind of fan heater, one unit of heat energy for 1 unit of electricity. A heat pump should be 4 times better than that if it's well, and even higher if you can keep the temperature boost down. So what that means from a sort of geothermal side, okay, I'm not a heat pump person, is that I know that I need to produce groundwater at the highest possible temperature for heating and at the lowest possible temperature for cooling, so I can make the heat pump as efficient as possible. That's my job as the geothermal person, and it's the building service engineer's job to make the heat pump work properly and all the rest of it. So that's kind of a constraint on me. Get that groundwater out as warm as possible, as cool as possible. So practically how these would work is that they would be really co-located with the buildings of interest. As we say, we can't transport heat a long way, so you would have some boreholes in an open loop system which would penetrate an aquifer beneath the building of interest. And then we would again produce groundwater from a well, pass it through the heat pump to provide heating, and then re-inject the waste back into the aquifer. And if we can get the wells deep enough, maybe we don't need to use a heat pump, as we've seen for some of those medium depth systems. Now, one of the things we can do, and I'm not going to go through, see, I'm a physicist, right? So there had to be 1 equation or 2 equations in the presentation, but I'm not going to make you go through it. All I'm going to say is this, right? We can make an estimate for sort of how far away that well can draw heat in. And if it's a flowing well, if it's open loop, we have groundwater flow moving in. And if we have to provide heating for about 6 months of the year, and I know how long the well is, and I know how much groundwater I'm going to produce, I can work out about how far away from that well we're going to be able to bring heat in. And typically it's around about 50 meters or 100 meters, something like that. So what that means is that I get lots of power capacity from the borehole. And really this will make more sense when we compare it with a closed loop system. But essentially open loop is great because you get lots of heat and lots of cool coming out of the borehole because you're able to transfer that with the flow of groundwater. The problem, of course, it's interesting if you're a geo person, is that you have to be able to predict flow through the aquifer with reasonably low uncertainty, to be confident that your groundwater flow is going to be fast enough and steady enough to be able to supply the heat or the cool that you need. So that's the bit that is great for geos, but it really puts building service engineers off. They get very worried about the idea the aquifer might not behave as predicted. And we can basically use this to provide heating or cooling or both, okay? So if we want to do heating, we basically produce water at the ambient aquifer temperature, pass it normally through a heat exchanger. We don't pass the groundwater itself through our heat pump. We take the heat out of it, and then we re-inject the cold wastewater back into the aquifer. And in summer, we can switch it around. We've produced groundwater at the ambient aquifer temperature. Now we take the cool out of it, and we re-inject the warm waste groundwater back into the ground. I'm going to show you a way of doing this that's better in a few slides' time, but this is the basic operation of an open loop geothermal system. If we don't have a good aquifer, okay, so all of this is assuming that we have a nice permeable porous aquifer available. That's not always the case. So in London, for example, if you're happy to go below about 80 metres, you get into the chalk, fantastic aquifer. But if you're not willing to drill deep enough, you've got a huge interval. We've got this 80 metres of London clay, which is impermeable, but you can still exploit that using closed loop boreholes. So if we don't have a good aquifer, we can use a closed loop heat exchanger, which basically works on the same principle. But now we have to rely on conduction to move heat in and out of the borehole. So we would typically have a U-loop, for example, where we inject down one limb and it comes back up the other. Or we might have a coaxial arrangement where you inject down the middle and it comes up the outside. And again, we can do a little back of the envelope calculation to say, well, how far away from the well can we actually get heat or cool into the well? And we can basically do that by assuming it's conductive and again assuming heating for about 6 months. And it turns out that we only get about 8 metres away from the well. So remember, for our open loop borehole, it was 50 metres. It's dropped right down to 8 metres if we have a closed loop well. So what that means is that we have a much smaller power capacity for each closed loop well, which basically means we need lots of wells to do closed loop. So open loop, we can use a small number of wells. Closed loop, we need to have lots and lots of wells to get sufficient heat or cool out of the ground. And this is, I'm going to skip this, it just tells you have to drill a lot of wells to get heat out. So in practical terms, what that means is if you have a large deployment, you will often find hundreds of wells that have been drilled. Under a car park, for example, there's an IKEA store in Sweden. Drive into the car park, there's lots and lots of manhole covers, and under each manhole cover is a borehole, it's a closed loop borehole which is sourcing heat and bringing it into the building. And they will design the array in such a way that you kind of maximize the efficiency with which you can get that heat or cool out of the ground. Okay, so that's the basic principle. For shallow geothermal, we bring this relatively low temperature fluids out of the ground, groundwater out of the ground if it's open loop. And we then take its heat or cool out using a heat pump, and then we pass the waste back into the aquifer. So the best we do is that we produce water at the ambient aquifer temperature. But what would be neater? Okay, so I said that in the summer, we're going to be injecting back into the aquifer waste heat. And in the winter, we're going to be injecting back into the aquifer waste cool. What if we reuse that? So instead of just leaving it in the aquifer, what if I store heat in the summer and produce that back out of the aquifer in the winter, and then store that waste cool in the aquifer and then bring it back out in the summer? And that's exactly what we do in underground thermal energy storage. So this is the energy storage bit, right? What I've talked about so far is geothermal. This is the energy storage bit. And what I like about this is it's more efficient than just leaving the heat or cool in the aquifer after we've used it, because we can bring it back out and reuse it. And remember, my job as the geothermal person is to bring water to the heat pump, which is as hot as possible for heating and as cool as possible for cooling. Now, if I just use the natural ambient aquifer temperature, I can't really change that. It's 13 degrees or 14 degrees. But if I reuse the waste heat and waste cool, then I can start to engineer it to give higher and lower temperatures for heating and cooling. So the two technologies that use this, one's called BTES, borehole thermal energy storage, and the other one is ATES, aquifer thermal energy storage. And that's the one I really like, okay, because it's big capacity and it's very efficient. So what we do in aquifer thermal energy storage, as I said, is that in winter, okay, we're producing groundwater, we're passing it through our heat exchanger, and we're using a heat pump to boost the temperature, and then we re-inject the waste cool water back into the aquifer. In the summer, we switch the wells around. So now, where we had been injecting, we now produce. And we produce cooled groundwater, and often it's so cool that I don't need a heat pump anymore. I can just cool the building directly with that cooled groundwater, and then I re-inject the waste heat back into the ground. So when you come into this from, as I did originally, I was a petroleum person, right? And we had injection wells and production wells. It was dead straightforward. And then when I went into geothermal, it was the same. We had abstraction wells and injection wells. Then I moved into this and it got really confusing because now the wells switch flow direction. And in fact, what we have is a cool well and a warm well. And the warm well is injecting in summer and producing in winter. And the cool well does the opposite. It produces in summer and injects in the winter. So we're switching the flow direction. These are bi-directional wells. We switch the flow direction. And this is great, right? Because now I can bring water out to my heat pump, which is hotter than the ambient groundwater temperature. So my heat pump's more efficient. And in the summer, I can cool and I don't even need to use a heat pump. So this is way more efficient than conventional geothermal. And if this little movie is going to play, it's not great resolution, but this is a little numerical simulation showing an ATIS system in action. This is the aquifer, and that's the building. And the warm plume builds out in the summer and then gets sucked in again in the winter. And the cool plume builds out in the winter, and gets sucked in again in the summer. So we're making these plumes of hot and cool water that grow and shrink as the seasons pass. And there are operating systems around the world, okay? So kind of typical deployments of ATES would be aquifer depths around tens to hundreds of meters. You have to have at least 2 wells, a warm one and a cool one, but these are often scaled up to have lots of wells, so lots of warm wells and lots of cool wells, so they can supply really big heating and cooling capacities. Flow rates of orders cubic meters an hour to thousands of cubic meters an hour, and they can power really big systems going up to tens of megawatts of heating and cooling. So a classical example is Arlanda Airport in Stockholm, which is heated and cooled by one of these ATIS systems, one of these big scale ATIS systems. Who is really doing this? This is a map showing different countries. You can maybe just about make it out. It's the Dutch. The Dutch have got about 3,000 ATIS systems operating at the moment. They are definitely the world leaders in deploying this technology. They have some fantastic aquifers, all sort of basically fairly recent river deposits because they have a pretty big river that passes through there. And the rest of the world is really catching up. There's a few deployments coming in now in Sweden and Norway and in Denmark, but we do actually have some operational deployments in the UK, and they're great because they act as demonstrators for this technology to build some confidence to apply it more widely within the UK. And if we look around the world, so I said that for electricity generation, geothermal contributes about 0.5%. But for heating and cooling, it's about 3.5%. So still a small number, but considerably bigger than electricity generation. So this is kind of why I think that heating and cooling from geothermal is like the unpopular younger brother of electricity generation. Actually, it's really good, and it's a bigger contributor to world energy generation, but very few people have really heard about it, and we don't really think about it as much as we should. And I think that this is really where we can make we can have a very large growth potential because we can do this shallow geothermal stuff almost anywhere. Okay, there's no need to be near volcanic systems or magmatic systems. You don't even need an aquifer. You can do it with boreholes in a tight rock near the surface. So for me, I'm kind of excited about geothermal for heating and cooling. It offers baseline, low carbon heating and cooling to buildings. It's very widely deployable. We don't have to frack, so we don't have these risks of seismicity. We can use naturally porous and permeable aquifers. And if we do it with energy storage, we can get very high coefficients of performance. We get cooling almost free and heating much more efficiently than traditional open loop geothermal. But the real thing here is that we need to be able to accurately predict how the groundwater will flow in the aquifers. That's why I like it so much, because that's what I like doing. I like understanding flow in the subsurface.